Hi folks, today we're going to discuss the article entitled Denoising Diffusion Probabilistic Models by, amongst others, Jonathan Ho. This article was published in December of 2020 and has been cited over 3,000 times. To understand this article, it's first necessary to develop some intuitions about generating images. Images, including generated images, especially those that are grayscale images, are really just matrices of pixel values between 0 and 255, whereas color images are images with 3 channels instead of 1, with each channel having a value of 0 to 255. Generative models are used to predict these pixel values based upon training, and such models are evaluated based upon such things as fidelity, which is the crispness of an image, and diversity, meaning the range of images that can be generated by the model. Applications of these models include the generation of synthetic data, which is, for example, content creation. To understand this article, it's necessary to understand the concept of latent variable models. So latent variable models are a class of image generation AI algorithms and include such things as generative adversarial networks, variational autoencoders, and diffusion models, which is the subject of this article. There are, however, other types of image generation algorithms, including autoregressive models, flow-based models, and energy-based models. The basic architecture of these latent variable models is that there's an encoder that reduces the complexity of the original image to fundamental features. There's latency space, which is a mathematical representation of the reduced original image. And then there's a decoder that increases the complexity to approximate the original image with respect to fidelity and diversity. The goal of these types of models is to create a standalone decoder that can take any image, including noise, and generate a diversity of images with high fidelity to the original image training set. All right, let's talk a little bit about generative adversarial networks, or GANs. GANs have, as I said earlier, an encoder that is comprised of a discriminator that basically receives a training set in the form of an image and makes a determination as to what that training set is, and then passes this determination to a cost function, where the cost function takes noise and the theta parameter and passes these two values to a generator, where the generator acts as the decoder, and the noise and the theta value act as the latency space. The generator then generates what's called an adversarial example and passes that back in to the discriminator, so the discriminator can make a determination as to whether that generated image is of the target class or not. So basically, there's an encoder that is a discriminator that determines whether the image is of a target class, and a cost function that provides the likely distribution of pixels as a theta value needed to create the target image. Then there's latency space, which is random noise used to generate the adversarial example and a theta value. There's a decoder, which is a generator to create the adversarial example to convince the encoder that the image is of a target class. And finally, in terms of how this encoder and decoder work together, it's really a sequence of freeze and repeat, where basically the encoder will generate a number of determinations to be used then to create the theta value, and then those will be passed to the generator, and the generator will continue to generate images until it can effectively fool the encoder, at which point then the encoder is unfrozen and retrained. As stated earlier, the goal of a latent variable model is to create a decoder that can be standalone, such that it can take an image, clean it up, and then present a generated image that has high fidelity to the original training set, yet is capable of diversity. Problems, however, arise for GANs in the form of something called mode collapse, where noisy images are passed in to the generator/decoder, and yet the generated image looks nothing like the noisy images, because effectively the generator creates images that are very similar or identical to the training set, thus manifesting a lack of diversity. Another type of latent variable model is a variational autoencoder. This is a U-shaped architecture that includes an encoder, a latency space, and a decoder. And of note, the input size of the original image must match the output size of the generated image. Further, the left side, the encoder, effectively downsamples or reduces in complexity the original image to certain fundamental features, whereas the right side, the decoder, upsamples this latency space reduced image to create a generated image, We'll discuss these concepts in more detail in the next slide. Some key ideas associated with variational autoencoders are that it's a U-shaped network that leverages convolutional neural networks as effectively subnetworks, where a CNN will reduce the complexity of the image and extract key features based upon probabilities associated with each feature. Really, this just acts like a filter. Next is the idea of convolutional neural networks transpose, or CNNTs, that really leverage the latency space to increase the image complexity to generate images with high fidelity and diversity. Further, there's just the latency space. The latency space is really a lower dimensional representation of the original image and can be illustrated by this two-dimensional graph shown here. Another aspect of variational autoencoders is that, like other latent variable models, their goal is to create basically a decoder that can create a standalone image with high fidelity and diversity. Problems, however, for VAEs arise in the form of posterior collapse, and that's where the decoder generates images that are disconnected from the input image, but rather are based upon noise. And so you can see here an illustration of basically an input image X that's passed in, but you get out a blurry image Y. The third type of latent variable model we'll be discussing today, and the model that is the subject of the article that we're discussing, is the diffusion model. This model has a UNet architecture like VAEs, but different than VAEs or GANs. It basically takes Gaussian noise to diffuse the original image to create a more uniform pixel distribution in the latency space, and we'll call this a forward process. Further, it has a process by which this Gaussian noise is removed to generate an image that is created with high fidelity and diversity. This is called the reverse process. And we'll get into each one of these, namely the forward process and the reverse process, in the subsequent slides. The forward process works by taking an original image and effectively adding, in a slow incremental manner, a small amount of Gaussian noise at each point in time. And so the Markov chain is basically a chain that depends upon the immediately preceding image. So for example, here you have P of Y that is generated from X at time 2, and P of Y that is generated from X from time 3, and P of Y that is generated from X at time 4. And notice there's no skipping from, say, for example, time 2 to time 4. Rather, it's purely sequential in nature. So what is this Gaussian noise? Well, really, Gaussian noise is created by a function that represents a distribution of many random variables as a symmetric bell-shaped graph. The advantage of Gaussian noise is it gives you a continuous predictable distribution of points on a graph. So as applied to the forward process basically has a goal of converting pixel values and distributions to a more Gaussian distribution. So for example, imagine that you have a distribution of pixel values for grayscale as shown here. You'd convert those over to a distribution that more approximates Gaussian noise, which is again this symmetric bell-shaped graph. Shown here is a particular pixel distribution where Gaussian noise is applied. So basically you have a sequence of Gaussian noise where one pixel distribution is dependent upon the immediately prior pixel position. This is the Markov chain idea. And you basically move from one position, say 110 to 175, to a second position at time 2, a third position at time 3, and then a final fourth position at time 4, where the pixel position is, for example, 145 or 150, and more closely approximates the Gaussian distribution as opposed to the original pixel position in its distribution. Now, as part of the reverse process, you basically use the prior noisy position to predict the next likely distribution of the noisy pixel position. And when you do this, you then minimize the difference between positions to generate an approximation of the original image data. Note that applying this reverse process, you eliminate the possibility of posterior collapse because basically all noise is Gaussian and it's removed as a part of this reverse process. So you can kind of see here how when using the reverse process, you go backwards from, for example, time 4 to time 3 to time 2, and then your original pixel position when you use the reverse process to generate an image. So shown here is more on the reverse process. And so you would start with a diffused image, And as you kind of move from left to right, you get an image that is clearer, crisper, has higher fidelity, and then in some cases is hopefully very diverse in nature. And that's your generated image. All right, let's talk about some refinements to latent variable models. So one refinement is the concept of controllable and conditional image generation. And this is applied to GANs and allows you to adjust a model to get desired outputs. So for example, if you're talking about a 3-channel color image, you can basically pass in some values to focus on particular aspects of the image to change, for example, hair color, or other features of the generated image. Another refinement is the idea of guided diffusion. So this is the idea of where you can basically do such things as take a text caption and use that text caption to generate an image. And so what's effectively happening here is that you're basically guiding the reverse process to create a particular outcome here based upon text input. Summing it up, latent variable models are a class of generative AI algorithms used for image generation and include such models as GANs, VAEs, and diffusion models. Diffusion models address some of the shortcomings of GANs and VAEs by controlling for the types of noise created and the removal of such noise. Diffusion models can create images that have superior fidelity and diversity when compared to images generated by GANs and VAEs. I hope you've enjoyed this presentation.